All right, so looks like we have a few slow quotes this morning, but we're going to start anyway. Okay. Happy Friday, everybody. Hopefully it's a good Friday for you. Kind of, sort of. Okay. So we have an exam tomorrow. We'll do a lot of review upstairs. Okay, but we'll finish chapter 8 today and then go from there. So right now we're still in chapter 8. We're going to go through periodic properties. Yeah, question?
I know you said that the test is going to be on chapter 5 through 7.
Yeah.
So is there going to be a little bit of chapter 8?
No.
No. Okay.
Yeah, it's just 5 through 7. So yeah, so this won't be on the exam for tomorrow. That'd be just cool. Okay. Okay, so we'll go through periodic properties, brief history of periodicity, Coulomb's law, and then the main bulk of this will be discussing periodic trends. So what is a periodic property? Well, when you go to the supermarket, when you think about when you go to the checkout counter, and you see these magazines on the rack, what do they call those? They call them periodicals, right? So they come out with regularity, they come out every time at a given time of month. So when you hear the word periodic, it really should ring a bell, like, oh, it's something that recurs in a pattern, over and over. So the periodic properties include, for atoms, they include atomic radius, ionization energy, and electron affinity. So these properties help explain and predict the reactivity of the elements. All right, so that's why it's important to know this. It's actually quite interesting. I'll show you a video a little bit later in regards to one of these. So a brief history of time, if you go back to the 1800s, there was a person by the name of Dmitri Mendeleev, and I'm not sure if I'm pronouncing that right, but I'm saying Mendeleev. He arranged the elements in order of increasing atomic mass, but not necessarily atomic number, which we'll get to in a little while. So he arranged the elements in order of increasing atomic mass. And if you look at the periodic table on the wall here, you'll notice that for the most part, the elements go in order of increasing mass. Right? Now, I mean, you've got hydrogen, atomic mass is 1, helium atomic mass is 4, lithium atomic mass is almost 7. Right, so for the most part, the periodic table is still arranged in the way that Mendeleev had originally put it. And they saw that certain sets of properties recurred periodically. Right, so by arranging the elements in the order of mass, they were able to observe similar chemistry for the given elements in a column. Okay. However, arranging the elements purely by average mass did not always line up with the observed properties. Okay, so based solely on atomic mass, which pairs of elements would be out of order? All right, so if you're going in order of mass, you see the elements up there that are out of order based on the mass. Well, let's look. Okay, it'll take you a little while to fish through, but if you look at iron, cobalt, and then you go to nickel, what do you notice as you go from cobalt to nickel? The mass actually decreases. All right, so so the masses don't always go in increasing order, but usually they do. Right? Can anyone spot another one? It'll take you a little while. Yeah, you see them? Yeah, tellurium, the Te. Yeah, Te, is actually slightly heavier on average than iodine. Right? So those are probably the two most common ones. Here's a couple more. Lawrencium and Rutherfordium are out of order. So if you go to Rutherfordium, where's Rutherfordium? RF, it's number 104. And Lawrencium is 103. So if you look at LR, 103, dark bottom right corner there, 262, Rutherfordium is 267, right? So that's out of order. And then there's hassium relative to meitnerium. Okay, so HS relative, let's see, 108, 109, those are slightly, actually those are, according to that one, they're in order. All right. I saw a periodic table the other day where it had them reversed. So just ignore this last one then. Okay, so clearly the elements don't always go in order of mass, but they do go in order of atomic number. So this led to, Moseley's discovery. So Henry Moseley was a physicist back in the early 1900s. This is actually after Mendeleev passed away. And what he did was he studied X-ray line spectra of many of the elements. And what he noticed was that the X-ray wavelengths of the excited metals he was looking at varied depending on the atomic charge. So he was looking at a series of X-ray lines that were in order of atomic charge based on the element. But he did notice that some integers of wavelengths were missing. Okay, and these turned out to be missing elements that had yet to be discovered. Right? So based on this observation, and they call these X-ray lines the K and L lines. If you ever hear about K and L lines, it came from Moseley's discovery. And so this led to a slight modification of the periodic table to arrange the elements in order of increasing atomic charge. In other words, the atomic number, not just the average mass. Okay, so that's how the periodic table is put together. So here's the thing, Mendeleev's periodic law helps us predict what properties an element will have, but it doesn't explain why the pattern exists. So why is the periodic table laid out the way it is? Why is that? Okay, and it's something we've been talking about for quite some time now. Chapter 7, what did we talk about? We talked about quantum theory. And in chapter 8, it was also about quantum theory, or quantum mechanics. So quantum mechanics is the reason why the periodic trends exist. Okay, so we're looking at, what do I mean by quantum theory? What am I talking about? I'm talking about s orbitals, p orbitals, d orbitals, f orbitals. Okay, these models that we've been discussing are all part of the quantum mechanical model. Okay, so knowing why allows us to predict why. So really you're going to use two things in this chapter. Okay, so a more complete explanation of the trends of the elements can be achieved by combining two things. One is quantum theory, and the other one is my favorite law of all time, okay, Coulomb's law. So it really comes down to these two things, okay, quantum theory and Coulomb's law. All right, so what is Coulomb's law? All right, we kind of talked about this before. Opposite charges attract, like charges repel. All right, so we're going to combine that concept with the quantum model as we go through the trends. As opposite charges go closer together, the attraction increases. As like charges get closer together, the repulsion increases. And increasing this magnitude just increases the extent of these attractions and repulsions. So if I ask you between calcium and sulfide, calcium ion and sulfide ion, versus calcium ion and fluoride ion, which one has a stronger attraction? Yeah, these two, because the extent of the charge is greater, right? All right, so just to review that a little bit. So there's something called effective nuclear charge, right? So this is sort of a Coulomb's law thing. It's the positive charge, quote unquote, felt by an electron towards the nucleus, right? So they call this term Z effective. And technically speaking, it's the atomic number Z minus some shielding constant. We talked about shielding earlier in this chapter. You can estimate this effective nuclear charge by just taking the atomic number minus the inner core electrons of an element. So let's look at some elements. So we have sodium. Atomic number is 11. So how many protons are in sodium? We have 11, right? How many core electrons are in sodium? I have here 10. Why is it 10? So if you think about the electron configuration of sodium, it's what? It's 1s2, 2s2, 2p6, 3s1, right? That 3s1 is the valence electron for sodium, but all the electrons before that are the cores. All right, so 11 minus 10 gives us a relative, an effective nuclear charge of about 1. Okay, so that's the effective nuclear charge that the valence electron will fill towards the nucleus. With magnesium, there are 12 electrons total in magnesium. Right, so that's 1s2, 2s2, 2p6, 3s2. That 3s2 means you got 2 valence electrons in magnesium, but you've got 10, you still have 10 core electrons. So for all these row 3 elements, they all have the same core electrons. Right, that's the quantum model. Okay, but there's also an increasing nuclear charge as you go through that shell. Right, so for a given shell, going from sodium to magnesium to aluminum to silicon, you're still in an n=3 shell. But the nuclear charge is increasing. So if you look at the radius, okay, the radius goes from 186 down to 132. Okay, why is this happening? Why are the elements getting smaller as we're going to the right in a row in the periodic table, right? Sodium, magnesium, aluminum, silicon. Right, there's more protons. So the electrons that do occupy that n=3 shell are feeling a greater effective nuclear charge to the nucleus of the atom. Right, so the atom's getting actually smaller, even though it's counterintuitive. You think, oh, an element with more protons, isn't it getting bigger? But it's the opposite of that. It's smaller. And it's because of Coulomb's law, right? The opposite charges are attracting. The nucleus is positively charged, the electrons are negatively charged. So the more protons you have in the nucleus, the more the electrons are sucked in towards the nucleus, making the atom smaller. All right, so Coulomb's law, but then it's also the quantum model, right? We still have core electrons versus valence electrons. That's a quantum mechanical concept. Questions about just that idea? All right. So speaking of atomic radius, atomic size, there's a trend that you need to know. And I made these diagrams to help you sort of navigate these kinds of problems. So atomic radius increases as you go down a column and to the left in the periodic table. As you go down a column in the periodic table, the radius is increasing because the extent of the screening is also increasing. The more core electrons that you have, the more that the outer valence electrons are repelled by those core electrons out. Does that make sense? So it's a screening issue as you go down the column. And as you go to the left in a row, you're decreasing the atomic charge in the nucleus. So less positive charge in the nucleus also makes the electrons able to expand out more. Okay, so when you study this, look at this diagram and read my notes here. Okay, because this explains the trend. Okay, it's a Coulomb's law argument. Okay, especially when you're talking about screening, that's a little more quantum mechanical. Okay, but it's also a Coulomb's law. Okay. So we're going to use that diagram as we go through this. Here's a sample problem. Arrange the following in order of increasing size. So here's how I strategize this. So I'm going to draw that diagram. Okay, this is the trend in increasing size, or radius. Oops. Okay, so increasing size, going down and to the left. And then you're going to take those elements and you're going to place them in this diagram. Where would chlorine be in the periodic table? You're gonna, it's as if you were taking this diagram and you're superimposing it onto the periodic table. So if I look at chlorine, it's in the upper right of the periodic table, right? So chlorine is going to be somewhere around there. And where would potassium be in the periodic table? And towards the left, but it's one row down from there. So potassium's down there. I wrote potassium here. Okay. And then where would sulfur be? Yeah, sulfur is just to the left of chlorine. And then cesium, where is that going to be? Below potassium. So if you're going to order these in increasing size, I think it's a lot easier to look at it from this way, right, to reason things out. So what's the appropriate order then in order of increasing size? Yeah, so of these elements, which one is the smallest radius? Is chlorine smaller than sulfur? Yes, because as you go down to the left, it gets bigger. Well, let's say in reverse. As you go to the right and up a column, the atoms get smaller, right? So chlorine is the smallest, followed by sulfur, followed by what? Right, followed by potassium, and then cesium is next. So this is your go-to, right? You take the diagram, superimpose on the periodic table, and it'll really help you visualize where you're supposed to go. All right. Questions? All right, let's do some more. What if you throw an ion into the mix? Okay, so when you throw an ion into the mix, this is my recommendation. Look at the neutral atoms first, do the same thing that we did in the first example, and then worry about the ion after that. Okay, so let's do that. So again, we're going to throw our diagram on the periodic table. Where does potassium fit in? Well, we know potassium is here. Where's calcium? Right next to it. Right. We have argon, and we got the right side. Okay. So let's go ahead and just order those in increasing size. Right, so we have argon, followed by calcium, followed by potassium. Okay, in order of increasing size. Okay, now we got 3, the last one to go. We have potassium plus. Do you think that's going to be, well, the easiest thing is, let's compare it to the neutral. How is potassium plus going to compare to potassium neutral? It lost an electron. Let's go all the way back to atomic structure. Which subatomic particle contributes most to the volume of an atom? All right, well, what are the subatomic particles? This is really basic stuff now. There's 3 main ones. Neutrons, protons, and electrons, right? Which one of those 3 comprises most of the volume of the atom? Electrons, right? The nucleus is really, really small, but it comprises most of the mass of the atom. But the electrons comprise the least amount of mass by a lot, okay? But they make up most of the volume of the atom. So when you take an electron off of potassium and make it potassium plus, you're going to make it a lot smaller, right? Or at least significantly smaller. So potassium is the smallest. Where does potassium plus fit into this?
Right.
Even smaller than potassium, right? There you go. All right, so one less electron relative to potassium nucleus. So it's a Coulomb's law thing and also quantum mechanical.
Is it supposed to go before the potassium neutral? Is it smaller?
Oh no, wait.
Potassium bigger?
Yeah, you're right. This is an order of increasing size. I was thinking of decreasing size. You're right, good catch. All right. Yeah, it does matter how, if they're asking for order of decreasing size versus increasing size. So yes, you're right. So okay, so why is argon smaller than argon, or why is potassium plus smaller than argon? So let's compare these two. So you have argon, and it has, how many protons are in argon? 18, right? We have 18 protons in argon. Okay, how many protons are in potassium plus? You got 19 protons in any potassium. All right, let's look at the electrons then. How many electrons are in argon? 18, right? How many electrons are in potassium plus?
18.
Same, right? 18. You got more protons pulling in the same number of electrons, and that's going to make it smaller than argon. And that's why it goes before argon. Good catching. You can see how it's easy to confuse it, right? You know, I mean, I did it right in front of you. All right. Okay, so argon is actually larger than potassium plus. So that's smaller. Okay. Questions? Okay, so yeah.
Does it, like, is it important for us to know which one has a bigger impact, going down and going left?
So for atomic radius, the radius is affected more by going down a column versus going across a row. So, I mean, if you had to compare differences in a column versus a row, you prioritize the column. And so the screening effects are greater than the nuclear charge effects. If I give something like this to you on an exam, it has to be something that's relatively reasonable to decipher. If they're all over the place, it's sort of hard to remember the numbers. There are atomic radius charts you can look up online, and I actually suggest you do that. Okay, take a look at the numbers and then reason out the why behind that. All right, so, okay. Any other questions? So that's radius. Oh yeah, here's another one. What if you have all ions? You're like, well, wait a minute, now we got to do them all. Okay, so this analysis that I did for argon versus potassium plus, you're going to want to do that for all the ions. So I recommend arranging them in order of atomic number and then looking at how the electrons compare. So if you have all ions, these charts are less effective. And it just gets easier to look at how these compare by their nucleus. So let's look at these and by their proton count. How many protons are in oxygen? 8, right? So oxygen has 8, right? Chlorine has 9. Nitrogen has 7. And then how many electrons do these have? This has 10. Fluorine or fluoride has 10, and nitride also has 10. So they all have the same number of electrons. It's just that now they're different by their proton count. So which one's going to be smallest? Which element there, which ion will be smaller?
Nitrogen.
Okay, so it's the opposite of what your intuition is going to tell you. Nitride has less protons in the nucleus. What does that mean for the size of the atom? It's not going to be as small. The electrons are going to expand out more. All right, Coulomb's law. Opposites attract. Okay? So arranging this in order of increasing size, it turns out that nitride is going to be the biggest. Followed by, which one is the second smallest? Oxygen, right? and then the floor, which will be the smallest. So this will be in order of increasing size. So it's the opposite of what you're going to go to. Like mentally, you're going to be like, oh yeah, that's smaller. It's smaller, right? Smaller number. No, it's the opposite, right? Smaller nuclear charge, bigger atom. Okay. So who cares about atomic radius? I always like asking that, right? Who cares? Oh, you had a question, Bob?
Yeah, how do you get the top numbers again? The 8, 9, 7?
That's the atomic number from the periodic table, right? So oxygen, atomic number 8, right? Fluorine, atomic number 9. That's the number of protons in the nucleus. It's going all the way back to your isotopes, right? Knowing your isotopes. So who cares about atomic radius? Well, it turns out that you have a lot of membrane proteins in your cells that will differentiate between ion size, right? So this is one example of how atomic radius or ionic radius affects physiology, right? So how do your muscles contract? They contract through something called a sodium potassium pump. Remember that from biology? Right, so that's just an example of how membrane proteins differentiate between ion size. Alright, so that's atomic radius. Okay, the second periodic trend we'll talk about is ionization energy. I just say IE. Do not confuse IE with inland empire. Okay, it doesn't mean inland empire. It means ionization energy. Well, you're from the IE? Yeah, I'm from ionization energy. Okay, so the energy required to remove an electron from an atom is what ionization energy is. So if you want to take an electron off of an atom, you're going to take you need energy to do that. Okay, it's an endothermic process. Okay, you have to put energy in to pull an electron off of that nucleus. Ionization energy increases moderately with successive valence electrons removed. So with every valence electron you remove, let's just say if you want to ionize an atom a second time, it's going to take you more energy to do that than it did for the first. So with each successive electron you're removing, it takes more ionization energy to do that. Now once you get to core electrons, then the ionization energy gets crazy high. Okay, it takes a lot of energy to remove a core electron. In general, ionization energy increases as you go up a column and to the right in the periodic table. So up and to the right increases your ionization energy. Unlike atomic radius, it's more prominent going across a row, whereas atomic radius is more prominent going down a column. Okay. So here's your box trend. Okay, so again, I love these because just superimpose them on the periodic table and think to yourself, okay, why is the trend the way it is? So as you go up a column, the extent of the screening now is actually decreasing. Okay, you've got less core electrons screening out those outer valence electrons. What is screening, by the way? I'm using the term, but let's just remind yourselves, what is screening? What is that? What is shielding? What is screening? What is that? Right, if you have a core electron, and you have this valence electron out here, how can the valence electron get closer to the nucleus if this core electron is in the way? Because remember, the nucleus is positively charged, electrons are negatively charged, but if you have other electrons competing for that nuclear charge, they're going to repel out these electrons trying to get in. Right? It's like going to the bar. Okay, if you were going to a bar and you're trying to get to that bartender to get a drink, but there's all these other people screening you out. Right? You know, so that's just an analogy. Don't go to the bar though. It's not but that's just an example, right? You know, so when I say the extent of screening is decreasing, going up a column, what I'm saying is the atom's getting that the nuclear charge is decreasing, yes, but also the extent of screening is decreasing. You're having less people at the bar, so to speak. You have less electrons in that atom, so there's less screening going on. Okay, and then as you go to the right in the row, you're increasing the nuclear charge, right? The atomic number is increasing as you go to the right. So there's your Coulomb's law. Okay, you've got the positive